This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are covering the topic composite bars, stress-strain relationship for the temperature. Generally, any metal when it is heated at a certain temperature, it expands. We are also observing in a railway track. In summer, the temperature rises nearly 45 degrees. The track will expand. Hence, in order to prevent its bending, generally some certain gap is provided between the two tracks. Otherwise, when the expansion is prevented, the internal stresses are developed in it, and resulting of this one, it will deform in such a way that the two tracks will not parallel to each other. And one more applications in composite cylinders, sometimes it is also called in thick cylinders, in order to withstand with the higher pressures, from the two different types of materials are made in the form of cylinders. One is inserted to another after heating now. So these are the two main applications of that expansion of the materials when it is heated for industrial applications. Here I am considering a bar as shown in figure here now. L is representing the length of the bar. Assume one end is in fixed, other end is free now. When it is heated at certain temperature, delta T, the length of the bar is increases by an amount of E as shown in figure. The total length now becoming L plus E. Since it is allowed to expand freely, and so there is no stresses induced in it. But when the same rod is, when it is prevented on both sides for expanding, when the temperature of the body increases by the same amount of delta T, that supports which are kept, which are not allowing to expand freely, that is compresses in such a way that the expected length of the expansions, what we have taken earlier E, that is the compresses to its original length. That is the preventing means here, it is the compressing now. That means when the temperature increases, when the body is not allowed to expand freely, that is compressed stresses are induced in the body now. Here this is shown in figure number 2 now. So the conclusion is, whenever there is some increasing in temperature or decreasing in temperature, it causes the body to expand or contract. If the body is allowed to expand freely without putting any supports, then the stresses induced in the body is becoming zero, but length of the object is changes now. But if the deformation of the body is prevented by keeping the supports, the stresses are induced, which are here now called thermal compressive stresses. Since these stresses are developed because of not application of any external load, it is only due to the change in temperature, and these stresses are called thermal stresses, or sometimes it is also called temperature stresses. Here, the thermal stresses in simple bars can be calculated as follows. First of all, calculate the amount of deformation that is taking place when it is heated at a certain temperature, by assuming that it is not at all having any support. That means it is allowed to expand or contract depending on change in temperature. The second is, after expanding, how much load that is required to keep the body in original positions that can be determined and calculate the strain, that is how much length that can expand because of change in temperature. If you know the Young's modulus, we can determine the stresses induced in the body. Since these stresses are developed only due to the change in temperature, hence these are called thermal stresses. Here I am taking an example here now. Let L be the representing the original length of the body at 0 degree centigrade, that means when it is not heated. Let T be the temperature that is increased now. Alpha is representing coefficient of linear expansion of the given object. Then according to the fundamentals of physics, the length of the body that is expanded due to the increasing in temperature is given by delta L is equal to L into alpha into T now, where L is the original length of the body, alpha is representing coefficient of linear expansion, and T is representing change in temperature. If the temperature is decreases, the length of the object is decreases. If the temperature increases, the length of the object is increases now. So when it is prevented, that means the delta L length of the object should be compressed, or in another words, compressive stresses are developed or induce the body when it is prevented to expand freely now. So the strain is given by the change in length by original length. Here delta L is the expected length of the deformation because of change in temperature. L is equal to total length of the body. Then strain is equal to delta L by L. It can be written as now alpha T now. Stress is equal to here now Young's modulus is equal to, we are having here Young's modulus is equal to, that is stress divided by strain. From these equations we can determine now stress is equal to a strain multiplied by the E now, that is Young's modulus. So here now it is equal to the product of strain multiplied by the Young's modulus. But the strain is equal to already determined alpha T now. Hence alpha T into E the stresses induced in the body. Since there is no external load is acting on it to induce the stresses, it is only because of change in temperature. These stresses are called thermal stresses, are also called temperature stresses. Sometimes before keeping the supports, some length is also allowed to expand freely. That is called here yield. Assume delta is representing, that is the amount of that bar is allowed to heal now. Then the actual expansion is equal to, it can be written as now delta L is equal to L alpha T minus delta. That means here delta L is representing how much the deformation that is taking place, or it should be compressed to get its original length. Then strain is equal to change in length by original length. It is equal to L alpha T minus delta divided by original length. It is equal to alpha T minus delta L. Stress is equal to, here it is a product of strain multiplied by the Young's modulus. So it can be written as now alpha T minus delta by L into A now. Okay, this is nothing but equations generally used to determine the stresses induced in the body because of change in temperature. Is the problem number 1. A alumina alloy bar fixed to both the ends is heated through 20 Kelvin. Find the stress developed in the bar. Take modulus of velocity and coefficient of linear expansion for the bar material be as 80 GPa gigapascal and 24 into 10 to the power of minus 6 per Kelvin respectively. Here I am taking here, this is nothing but aluminum bar. Here both the ends are there now, they are fixed now. The given the problem is the increasing in temperature is equal to 20 Kelvin is given. The modulus of velocity is equal to 80 gigapascal. It can be written as 80 into 10 to the power of 3 Newton per mm square. The coefficient of linear expansion is equal to alpha is equal to 24 into 10 to the power of minus 6 per Kelvin. So the thermal stresses developed in the bar is equal to sigma is equal to alpha into T into E now is given, which is equal to alpha is equal to 24 into 10 to the power of minus 6. T is equal to change in temperature is equal to 20 Kelvin is given. E is equal to 80 into 10 to the power of 3, which is equal to 38.4 Newton per mm square. It can be written as 38.4 MPa now, megapascal now. So, even though these external forces are not acting on the body, the stresses induced in the body because of change in temperature, that is increasing in temperature 20 Kelvin, the stresses induced in the bar is equal to 38.4 megapascal. Here problem number 2. Brass rod of 2 meters long is fixed to both the ends. If the thermal stresses not exceed to 76.5 megapascal, calculate the temperature through which the rod should be heated. Take the values of alpha and E as 17 into 10 to the power of minus 6 per Kelvin and 90 gigapascal respectively. Here a brass rod is given again. Yes, it is fixed at two ends as shown in figure now. The length of the bar is equal to is given 2 meters. So, length of the bar 2 meters. 2 meters nothing but it is equal to, we can written as now 2 into 10 to the power of 3 mm. Maximum thermal stress is equal to 76.5 megapascal. It can be written as 76.5 Newton per mm square. Alpha is equal to 17 into 10 to the power of minus 6 per Kelvin. E is equal to is given 90 gigapascal equal to 90 into 10 to the power of 3 Newton per mm square now. Here we require to calculate the temperature through which the rod should be heated. T is required now. Hence, let T be the temperature through which the rod is heated in Kelvin. The maximum stresses induced in the rod is equal to 76.5, which is equal to, according to the formula, alpha T E now. That is alpha is equal to coefficient of thermal expansion, which is equal to 17 to the 10 to the power minus 6 into T into 90 into 10 to the power 3, which is equal to 1.53 now. Therefore, T is equal to 76.5 divided by 1.53, which is equal to 15 Kelvin now. That means when the temperature reaches 50 Kelvin now, the stress induced in the bar is 76.5 megapascal. This is our required answer. There are two parallel walls, 6 meters apart. That is here now we are giving now it is one wall. There is one more wall is there. These two are 6 meters apart are stayed together by the steel rod 25 mm diameter. That is 25 mm diameter. The length is given now here. It is equal to 6 meters now. The nuts are tightened home when the rod is at temperature of 100 degree centigrade now. Determine the stresses in the rod now. When the temperature falls down to 60 degrees, if A, the ends do not heal now. The second way, the ends healed by 1 mm. Here, after heating, since the nuts are tightened together now, afterwards the temperature is decreasing now. That is, the supports are, or the nuts are always just pulling the rod to maintain a distance of 6 meters apart. Hence, the stresses induced in the bar is tensile in nature. So the given data in the problem is length of the bar is equal to 6 meters, that is 6 into 10 to the power of 3 mm. Diameter is equal to 25 mm is given. Decreasing in temperature, that is change in temperature is equal to 40 degrees centigrade. Amount of yield is equal to 1 mm is given. Modulus of velocity 200 gigapascal, which is equal to 200 into 10 to the power of 3 Newton per mm square. And coefficient of linear expansion given 12 into 10 to the power of minus 6 per degree centigrade now. The stress, here we have to calculate the stresses for the two types. When there is no yield allowed, the second one is when 1 mm yield is allowed now. The case 1, the stresses in the rod when the ends do not heal now. It is given by alpha into T into E now. And substitute the values, alpha is equal to 12 into 10 to the power of minus 6, T is equal to 40, here 200 into 10 to the power of 3, that is the Young's modulus. From this relationship we got to 96 Newton per mm square, which is equal to 96 megapascal. That is, here the stresses which are induced in the bar are in tensile in nature now. The second case, the stresses in the rod when the ends yield by 1 mm is given by, that is sigma 2 is equal to alpha T, that is the expansion that is allowed, minus delta divided by L into E. This is called the air now, the strain which is produced now. By substituting these equations now, alpha is equal to 12 into 10 to the power of minus 6 into 40 minus 1, it is there now, and divided by L is equal to 6 into 10 to the power of 3 into E is equal to 200 into 10 to the power of 3. From this relationship we got it is equal to 62.26 megapascal, or it is also equal to 62.6 Newton per mm square now. Thermal stresses in the bars of circular tapering section. Here the bar taper sections, here it is one end that is called here bigger end, it is having diameter T1, and the other end it is D2, that is decreasing in diameter, such that it is tapered uniformly entire its length. Let L be the representing the length of the bar now. So here we have to determine what are the thermal stresses induced in the taper sections when it is heated at a certain temperature. Here the data, given data, assume in the problem is L is equal to length of the bar. D1 is representing the diameter at the bigger end of the bar. D2 representing diameter at the smaller end. T is representing increasing in temperature, and alpha equal to coefficient of expansion of the materials. As a result of the increasing in temperature, generally the body expands. But here when it is prevented, the thermal stresses are induced in it now. The increasing length due to the increasing temperature, the equation is delta L is equal to L into alpha into T now. This is the equation number 1 now. But according to our previous problems, if P is nothing but the load which is applied on both sides, as it is there. So, in this case, if P is the load that is applied to bring the deformed body to its original length, and according to the formula, that decreasing length because of the supports kept at its two ends given by delta L is equal to 4PL divided by pi into E into D1 into D2 now, where delta L is nothing but that is expansion of the body when the temperature raises to T, where P is the load that is act at both the ends to bring the body to its original shape. E is representing young smallness, D1 and D2 representing the diameter of the rod at bigger and smaller end respectively. Since this equation number 1 and 2 are both the same now, from this relationship we got L into alpha into T is equal to 4PL divided by pi into E into D1 and D2. Here from this relationship, here LL get cancelled now. P is equal to, we can write it now, that is alpha T multiplied by pi E D1 D2 divided by 4 now. Or from this equation, maximum stress is equal to, maximum stress induced in the bar is equal to force divided by minimum area. Minimum area is equal to nothing but at this position, at B and position it is having minimum area. And so we can take it as alpha into T into pi E D1 D2 divided by 4 divided by pi dt square by 4 now. From this relation we got to alpha T E D1 divided by D2. This is our required answer, that is the maximum stress induced the bar can be determined. Now the related problem is problem number 3. A circular bar rigidly fixed at its both the ends, uniformly taper from 75 mm at one end to 50 mm at the other end. If it is temperature raises to 26 Kelvin, what will be the maximum stress develop in the bar? Take E is equal to 200 gigapascal and alpha as 12 into 10 to the power minus 6 Kelvin for the bar materials. Okay, the given data in the problem is the diameter at the bigger end. We are calling it as here end 1 now. It is equal to D1, it is equal to 75 mm. The diameter at the smaller end, that is a 2 position, it is equal to 50 mm. The change in temperature, that is increasing temperature, is equal to 26 Kelvin now. So E is equal to 200 gigapascal, 200 into 10 to the power 3 Newton per mm square, and alpha is equal to 12 into 10 to the power minus 6 per Kelvin now. The maximum stress developed in the bar is given by the equation alpha into T into E D1 divided by D2. Just substituting these values in this equation, we got 93.6 Newton per mm square, or it is also equal to 93.6 megapascal. Thermal stresses in bars of wiring section. Here in previous problems, the diameter of the bar at one side is bigger and other side is smaller, but it is tapering just uniformly entire its length now. But in this problem, it is in the form of 2 bars having just different diameters, the connected together as shown in figure. That is AB is having one diameter and BC is having one more diameter. That is, we have to determine the thermal stresses in this bar, in which the cross section is varying at different locations. Now consider this ABC bar of a varying cross section as shown in figure. 2 ends at A and C, it is having supports, that is fixed to prevent expansion when it is heated. L1 is equal to length of the bar of portions AB, and L2 is representing length of the bar BC, and sigma 1 the stresses induced in the section 1, that is the AB, and A1 is the area of the cross section of the section AB. Similarly, L2, sigma 2 and E2 are the corresponding values of section 2 now as shown in figure. As a result of increasing temperature, the bar ABC will tend to expand, but since both the ends are fixed at A and C position, therefore it will cause same compressive stresses in the body. Here, the compressive stresses, it may be the different at a different sections A, B as well as the B, C, but the amount of load that is the compressing, it is the same in two sections. Sometimes if it is having three or more sections, the load is treated as the same now. Hence, the thermal load, what is the called this load? Thermal load, that is nothing but the load which is applied to bring the body to its original shape, or which is preventing its expansion, is shared equally at both the portions, that is the section 1 as well as the section 2 now. That is, here just if I take the free body diagram of this figure like this, here it is the one section, it is one more section, it is there, that is A, B and C. This is nothing but treated as P and P as shown in figure now. That means it can be written as now, it is AB and second section is there now, it is B, C, but it is having like this now, P, P, P and P and so on now. Hence, the thermal load nothing but sigma 1 already were taken, it is the stresses induced in the section AB, and A1 is the area of the cross section. So the thermal load that is developed in a portion AB is given by sigma 1 A1, it should be equal to sigma 2 A2 now. The total deformations, it is given by sum of the expansion that is taking place in section AB as well as the BC. Hence, delta L is equal to delta L1 plus delta L2, which can be written as now sigma 1 L1 divided by E plus sigma 2 L2 divided by E now. So, sigma 1 L1 plus sigma 2 L2 divided by E. This is the total deformation taking place in a bar in which the cross sections are varying now. Sometimes the modulus of elasticity is, if it is a different, because if it is a made up of one materials now, aluminum, another one is with the brass, we are taken now like this, that is the Young's modulus, if it is a different, the total expansion is given by sigma 1 L1 divided by E1 plus sigma 2 L2 divided by E2 now. That is the expansion taking place in each section is determined separately, and the total expansion is equal to the algebraic expansion that is taking place in section 1 as well as the section 2 now. Now, taking just example just based on varying section, a steel rod ABC is the formally held between two rigid supports A and C as shown in figure. Find the stresses developed in two portions of the rod when it is heated through 15 Kelvin. Take alpha is equal to 12 into 10 to the power of minus 6 Kelvin and E is equal to 200 gigapascal. Okay, the given data in the problem is here now. Area of the portions 1 now. Here assume this is the portions 1 now. And is the portion 2 now. A1 is equal to, is given now, that is 400 mm whole square. The length is given, that is 500 mm L1. Similarly for the 2, the area is given 600 mm square. L2 is equal to 800 mm. The temperature raised is equal to 15 kilonewtons. The coefficient of linear expansion for the both the section is 12 into 10 to the power of minus 6 per Kelvin, and the modulus of elasticity is equal to 200 gigapascal. It is equal to 200 into 10 to the power of 3 Newton per mm square now. Let sigma 1 is representing the stress induced in the portions AB and sigma 2 in the portions BC. Then the thermal load shared by the sections AB as well as the BC both are equal, which is equal to, thermal load is equal to sigma 1 A1 is equal to sigma 2 A2. The stress developed in the portions AB is equal to sigma 1 is equal to, from this relation, sigma 2 A2 divided by sigma 1, which is equal to sigma 2 into 600 divided by 400, which is equal to 1.5 sigma 2 now. Now, let delta L1 is representing the free expansion of the section AB when it is allowed to expand freely without having any supports at its end position. It is given by alpha 1 L1 into alpha into T, which is equal to 500 into 12 into 10 to the power of minus 6 into 15, which is equal to 0.09 mm. Similarly, for the second section, delta L2 is equal to L2 into alpha into T, which is equal to 800 into, that is length of the bar is equal to 800 into alpha is equal to 1200 into 10 to 12 into 10 to the power of minus 6 into temperature raise equal to 15, which is equal to 0.144 now. The total expansion the rod is equal to delta L is equal to delta L1 plus delta L2, which is equal to 0.234 now. Let a compressed load that is applied at A and C now, which will cause the contractions of 0.23. Let here now P be the compressive force that is applied at both the ends to compress a rod of how much is 0.234, that is nothing but to keep the body in original shape. Then according to the formula, total expansion is equal to, we can take it as now, that is sigma 1 into L1 plus sigma 2 L2 divided by E now. Since sigma 1 is equal to already we determined, which is equal to 1.5 into sigma 2, L1 is equal to 500 plus sigma 2 into 800 divided by E is equal to 200 into 10 to the power of 3 now. From this relations we got now 7.75 into 10 to the power of minus 2 into alpha 2, or from this relation we got to sigma 2 is equal to 30.2 Newton per mm square, which is equal to 30.2 megapascal. Similar, sigma 1 is equal to 1.5 sigma 2, which is equal to 1.5 into 30.2, which is equal to 45.3 megapascal. Here the thermal stresses induced in a composite bars now. Here composite bars means the two bars are held together in such a way that when they are heated or when the temperature decreases or just cooling is taking place, the expansion as well as the contractions of both the bar is always the same now. Here now consider the composite bar consists of two members, a bar as well as the bar of steel, another one is the brass as shown in figure now. Here, since the coefficient of linear expansion of the brass is more than the steel now, when these two bars are separated and heated to the same temperature, the length of that is expansion of the brass bar is more than the steel bar now. Here, which is represented here now in figure number 2. But when these two bars held together such that both the bars should be expand or contract depending on change in temperature, having this equal now, because they held together now. So both may be just expand the same length or it may be the contract the same length because of change in temperature. But if we observe, since the length of the bar, that is brass bar is more now, it is expanding. That means when it is joined together now with the other materials, it is not at all expanding that length now. That is, the steel bar is nothing but it is not allowing to expand more length because it is rigidly fixed. Hence, in brass bar, generally, that is compressive stresses are developed in it now. Similarly, the brass bar is always since having more in linear expansion, it is always tried to pull the steel bar to increasing it some more additional length. Even though its free expansion is lower than that one now, because of brass materials, it is expanding more in length now. Or in other words, in steel bar, that the tensile stresses are inducing now. So this is shown here now in figure number C now. That is, let the bar be heated through same temperature. If the component of the bar, that is steel and bars, would have been free to expand, then no internal stresses are induced in it. But the two materials, when they are rigidly fixed now, therefore the composite bars will not expand by the same amount when it is allowed to expand freely now. It is obvious that the brass will be subjected to certain compressive force now, and whereas the steel is subjected to tensile same force as shown in figure C, what we discussed now. Let sigma 1 is representing the stresses in the brass now, and epsilon 1 is representing strain is brass, alpha 1 is representing coefficient of linear expansion of the brass, A1 is the area of the cross section of the brass. Similarly, sigma 1, epsilon 1, alpha 1, A1, that is sigma 2, epsilon 2, alpha 2, and A1, A2 are the corresponding values for these steel materials. Since both the materials having expanding or contracting the same length, let epsilon is representing the actual strain of the composite bar per unit length. Therefore, the load which is acting on both bars is same, but nature it may be different now. The force which is acting on brass bar is compressive nature, but in steel it is a tensile nature. But the magnitude of the forces which are acting on both the bars is same now. Hence, we can take it as a sigma 1 A1 is equal to sigma 2 A2 now. So, the strain in the brass is equal to, it is given by sigma 1 is equal to epsilon alpha 1 into T, that is nothing but what is the free action taking place. But actually, it is nothing but epsilon, we have to take it now. For the steel, it is nothing but here plus is required now. So, adding these two equations now, that is the total expansion is given by epsilon 1 plus epsilon 2 is equal to, then nothing but adding these two, we got it now, T into alpha plus alpha 1 plus alpha 2 now. In the above equations, alpha 1 is greater than the two values of alpha 1 and alpha 2 now. The values of strains, that epsilon and epsilon 2, also find out from the relationship of modulus of velocity now. So, after getting the strain now, the stresses can be developed by using stress and strain relations now. Okay, thank you, sir.
Like, share and subscribe. Hit the bell icon for more updates.